Hello, everyone, to another OCP Tap call. This is call number 120. Today we have Pat Heelan. Pat Heelan has been building distributed systems and databases since 1978 at companies including Tandem, Microsoft, and Amazon. He's constantly curious about merging trends in technology and their implications on systems. Pat has been working on database technologies at Salesforce since 2012. And also we have Daniel May. Daniel works at Salesforce and has been analyzing and improving the performance of complex systems for more than 7 years. Spent much of his spare time voraciously consuming technical papers, largely about distributed systems. So today's talk is titled Yours, Mine, and Ours. And with no further ado, Pat and Daniel, the floor is yours.
Thank you. Hi, I'm Pat Helland, and here's Daniel also.
Hello.
And the talk is titled Yours, Mine, and Ours because this is about set reconciliation. If we have two different systems with the same set with only slight differences, how can we find those differences efficiently and rapidly? And so we kind of thought that was a fun title. By the way, the little rectangle in the corner with our names is because we're going to PowerPoint record our faces in that little corner. So we allocated space, that's all. And so these are our own ideas and not necessarily reflective of the position of our employer, Salesforce. Daniel and I both work at Salesforce. So we'd like to do an introduction and talk about the problem we hope to solve and why we think it's important. And this was driven by a paper that we found at a SIGCOMM just in August of last year. We saw it a few months earlier, called Practical Rateless Set Reconciliation. And we pounded for a long time to understand the paper. And this is our explanation of the ideas that are in it with some different nomenclature and stuff. We'll talk about that. Then we're going to say why we think this is super valuable and discuss emerging opportunities and conclusion. And especially, we do think this is relevant to time. We do think this is relevant to emerging understandings of common knowledge, who knows what, when did you know what, and all of those things. But we'll dig into that after we explain this really unusual algorithm and why it's so cool. So let's talk about set reconciliation. As I said, there's this new paper from SIGCOMM, and it's called Practical Rateless Set Reconciliation. And the algorithm they describe is a variant of fountain codes. And if you're a networking guy, you're kind of used to fountain codes. They're a forward error correction where you keep sending information until the other side eventually says, gee, I got enough. Imagine talking to the Voyager spacecraft, light weeks away, and then eventually it says, that stuff you told me 3 weeks ago, I actually understood it. Now you can stop sending it again. And so this is also about fast set reconciliation. That's one way of viewing the thing it does. So you want to take the symmetric differences. If I have a set A with a bunch of items and a set B, how can I find the stuff that is in A and not in B and the stuff that's in B and not in A? And this algorithm is useful for very large sets with relatively small differences. And the point is it's less than order n log n work for n being the size of the difference, not the set. That ends up being kind of really fascinating when you think about it. Well, who cares about sets? We're databases and distributed system people. What's this set crap? We don't care about that. Well, we're going to argue that this is magic for databases and distributed systems because you can rapidly and accurately communicate changes in a system. You can repair data discrepancies, anti-entropy, this replica is missing this, that kind of thing. You can gossip state, and you can optimize multi-phase protocols. Now, interestingly enough, that optimizing multi-phase protocols assumes you can say, a notion of time and what was known in a window of time. So we have to dig into that. This is relevant to time. Did you want to add anything about time in there, Daniel? I know we were talking about that.
Yeah, absolutely. I think that in a lot of our previous discussions that we've been excited about this because with the combination of the proliferation of atomic clocks and potentially some of these clever algorithms to take advantage of things like epochs or just more precise time bounds, we're very excited about the idea that there might be some non-local optimizations that could be made in the distributed system space. So I'm here to explain why you already care about set reconciliation. That essentially a lot of databases and distributed systems have a recurring flavor of algorithm, which is just finding and eliminating differences. So this can show up with anti-entropy protocols. So for example, when, let's say, the database Cassandra consistently tries to find and eliminate any differences between its replicas. In addition, a lot of quorum evolution, or basically the ways that we evolve our systems by adding and replacing strategically servers, is also predicated on needing to be able to quantify and eliminate any differences in the data between replicas. Our perspective on this is error correcting by any other name. So there's some familiar techniques to be able to handle this. So for example, Merkle trees are the most classic, which requires, unfortunately, n log n or log n round trips to be able to crawl down the tree structure to be able to find what the minimum set of differences are. Because of this, we often see a non-local design decision made to force things into being more log-based. It's a lot easier to reconcile if there's already a total order of all of the events that have transpired in the system. This is an exciting algorithm because it allows us to take a step back and reconsider with a stronger reconciliation protocol what other design decisions can be made.
So what is our perspective of this practical rateless set reconciliation? Goal number one is to explain this thing, which I personally was gobsmacked at. I was just like, oh my gosh, that you can take two extremely large sets. Like, one application a friend of mine pointed out is, gee, if you have a genome with 300 billion entries in it and you want to compare genomes, and this is not proportional to 300 billion, it's proportional to the 2,000 things that are different. That's astonishing. The paper took work for us to understand. It really did. And it took more work to explain it. And we're standing back and trying to make it approachable to understand how and why this works. Goal two is to inspire thoughts about how to use set reconciliation in surprising ways. We want to start with some stuff we've thought about what this could be used for, and then get discussions going and brainstorm with smart people about other ways set reconciliation can change distributed systems. What do we mean by sets? It's a set of many items. What is an item? It is a fixed length thing with unique item values in it. Maybe it's 100 bytes, maybe it's a kilobyte. The bit pattern is unique. The set item is unique. This is not key values. You do not update an item. An item is not in a set and then it's added into a set. You can build things on top of that. You could build a key value on top of it. You could build a database on top of it. But this algorithm is about the presence or absence of items in a set. And they're fixed length, the way the algorithm is described. We know we can extend it to variable length, but we're not going to talk about that. So items are added to a set. They are never deleted and they are never updated. You can make an empty set. You can make a set for stuff you're going to do next Tuesday or next year. You can make a set for things with this category and that category, and it's empty, and then items appear, but they're never deleted and they're never updated. Set reconciliations to find the missing items. If I have set A and I have set B, what items are in A and not in B? What items are in B and not in A? So we want to explain, if you do go to the paper that we're citing, the nomenclature differences so our talk doesn't get you tangled up. The paper has a set of terms, and we kind of changed some of them because we think it's more approachable. The term in the paper is coded symbol. Our talk talks about it as a slot. The term in the paper is a source symbol. Our talk calls it an item. In the paper, there's an index. We call it a slot number. And in the paper, they talk about subtracting source symbols. We're going to talk about merging slots. Merging is not exactly subtracting. Merge uses XOR to take the symmetric difference. And merge actually concurrently adds and subtracts items from a slot. We will explain this. We will go into it. I just wanted to highlight, if you go to the paper, don't get too tangled up that the nomenclature is different. Okay, let's talk about our concepts. And we're going to then go, in the paper, we're going to talk concepts. We're going to introduce items and slot sequences, items and slots. How do you encode a representation of a set? How do you find, and then how do you decode from the set? And then the magic starts to happen about the set difference and explaining how that works. And then we'll summarize the thing in this section. Well, I'm going to give you some inspiration. XOR can find one missing value in order one time, assuming there's only one. So imagine Daniel's got a set of 1 million items. I have the same set of 1 million items, but I've added one. I can then take the XOR of all of those million plus one items and I send it to Daniel. If he XORs it with his million, boom, out pops the one that is different. Let me show you how that would work. Okay, so I have set A and Daniel has set B, but there's one thing missing. The item B is missing from Daniel's set and is present in my set. I've XORed together everything in my set. And here I've got, 7 items. It could be a million. It doesn't really matter. And Daniel's got 6 things XORed together. And now if we XOR the 2 of them together, what magically pops back out is the thing which is not in both, because the things that are in both cancel out with XOR. So that's the inspiration and the magic. The problem here is, well, that's fine for one, but what if there's more than one? Is there a pattern for encoding the logarithmic set that can find that set difference in order n log n of the difference, not the set size? And this algorithm is a variant of erasure coding, specifically fountain codes, forward error correction for message transmission, and it's kind of a cross between data communications error recovery and storage error recovery. But the fascinating thing is we're observing erasure codes are not just for data you've lost. They can be for data you do not have yet, and that ends up being a different way of thinking about it. So this paper, Practical Rateless Set Reconciliation, SIGCOMM, here's the authors, Yang, Gilad, and Alazada, and it's called Practical Rateless Set Reconciliation. And they talk about the symmetric difference, large sets, small differences, and order n log n of the difference. Reconciliation is the worst case of that. So what do we mean about set difference? Server A has set A. Server B has set B. They're mostly the same, but there's some differences. Server A starts sending an encoded representation of its set, a small prefix of an encoding. And we're going to explain this is an infinite encoding, but you don't send all of it. You send a prefix. When enough of it gets to B that B can tell what A has and B doesn't, and vice versa, it says stop. So the interesting thing is the symmetric difference, which is the items in one set, but not both. And if there is a tiny difference, you don't need to send much of the encoding, and you don't need to do much computation. That's kind of the magic we want to talk about. And this is observing the applicability of erasure codes to sets that don't actually exist yet. Just agree on what the set is. The paper describes an analysis claiming excellent performance, and it points to an open source implementation of the algorithm. And that's just fine if you want to go dig into it, but we're going to point out the things we think are interesting within it. So what are the goals and underlying techniques? The goal is efficient set operations and reconciliation. Again, 2 sets of fixed length items, set A and B. Items are fixed length, but they can have a different count. B has more than A or A has more than B. The underlying techniques are symmetric difference, and we're going to apply that both for the items in the sets and the items in the slots. I have not explained slots. I will explain slots. We write that as A delta B as the symmetric difference. So the one technique is symmetric difference. The next one is pseudo-random sequences. I'm going to take an item, I'm going to deterministically map it to a sequence of slots that's infinite. And you can deterministically regenerate that sequence based only on the item itself. We'll explain this. I realize I haven't explained it. And then the third technique is exponential distribution. So as the new slots of a sequence for a single item come, they have ever larger gaps. That means you have rapidly dropping probability of colliding with a slot from another item. I'll show you more in gory detail. First, some concepts and terms. An item is a fixed length unique set element. And we include in that a hash code derived from the item for error checking, amongst other things. And you can extend it to variable length, but we're not going to talk about variable length. It's fixed length for this discussion. Now, what is the prefix of an encoded set? You take a bunch of items and you're going to encode them, but that encoding actually is designed to go on infinitely, but you don't have to send all of it. You send the beginning of it. The more stuff you put in, the smaller the the less stuff, the smaller the beginning, the more stuff, the bigger the beginning. And it is a sequence of slots identified by their index, and each slot encodes 1 or more items, or actually 0 or more. We'll talk about that. And the slot contents and the slot index are transmitted in increasing order starting at slot 0. Empty slots cost nothing to transmit because each of them's got an index number. You can skip over the indexes. What is in a slot? It's an element of an encoded prefix of a set, including its index. the contents of a slot with 0 or more items, you take each of the items that's landed in the slot and you XOR them together. Remember, they're fixed length. They could be 100 bytes, they could be 1,000 bytes, they could be 100,000 bytes. You have to design that when you're building your solution for this. But you take the items that have landed there and you XOR them together, and that's the item sum. Each individual item you hash. So you now have, if you have n items in the slot, you have n hashes of the individual items before you XOR them. And now you have a hash sum which XORs those hashes. 3 interesting cases for a slot. Nothing's in it, no items, it's an empty slot. 1 is it, it's referred to as a pure slot, exactly 1. More than 1, it's an impure slot, and we'll be able to tell that difference. When you merge 2 slots, you're XORing the contents together, and it can actually increase or decrease the items in the slots that are there, and we'll explain how that works. Finally, there's this per item sequence of slot indexes. I start with an item, and I end up getting these indexes that say, where will that item land? And those 2 tricks we use, pseudo-random, I start with the item as a seed, so its slot sequence is identical every time I go with that same item. And it's exponential because we increasingly create a greater stride across the slot indexes by approximately 1.5. Show you that right now. We're going to talk about items and slot sequences. Every item maps to an infinite sequence of slots. What the heck are we talking about? Exactly 1 item, I'm going to figure out the slots that it might land in. Everything lands at 0, so that's a rule. Now I use pseudo-random stuff. Take the item, I'd hash it, and I use it as a seed to a pseudo-random number generator. That means for this item, I'm going to get the same slots over and over again every time I try. Started with the item, got the hash, got the seed of a pseudo-random generator. Then I'm going to use some arithmetic tricks to get exponential gaps as we go. So now it's deterministic. Give me an item, I get the hash, I get the pseudo-random thing, and I get the same sequence of slot indexes. Now, each slot is going to be collided based upon different items. Did more than 1 land there? If there's nothing there, we can tell because the item sum 0 and the hash sum is 0, and so nothing landed there. If there's exactly 1, we can tell because the hash is actually the hash of the item sum. So we know that only 1 thing's there. If the hash sum is not equal to the hash of what I have for the item sum, then something went wrong, and didn't go wrong, but more than 1 thing landed together and was XORed into a mush. The larger the slot index, the fewer the items statistically land, more become pure and more become empty. The beginning of an encoding is very dense. It's got everything, and then just more and more. The tail of it becomes sparse. So we're going to show you how that works here. It's an infinite sequence of slots per item. Each item maps to an infinite sequence, starts at 0, and then you have to say, how far do I go to the next one? How far do I go to the next one? So I'm going to calculate a gap by taking the pseudo-random number generation of the item. Talk about that in a sec. Pseudo-random number generators. The seed equals the item's element, and it gives me a sequence of random values from 0 to 1. And I square it, and I square root it, and then I 1 over the square root, now minus 1, and that gives a distribution centered on 1.5. I use that to calculate the next index. So this thing landed at 0, I add 1, and then I multiply it times the gap, which is this stride of the distance. So each time I get a new one, it's going to be about 1.5 times as far away as the idea. So the gap distribution impacts the coding density. 1.5 is actually close to the theoretical Shannon limit, but rounding it to 1.5 is good for computational efficiency. And there's a lot of fun material in the paper on that Shannon density and the Shannon limit of theoretical communication. But let's motivate it. There's a PowerPoint description to kind of make it make sense. Each of these columns, 0, 1, 2, 3, the columns represent slots. And this goes up to slot 42 only because I wanted the PowerPoint to be pretty and I ran out of room in the PowerPoint. If I'm going to encode item A, I take item A and I hash it and I feed it into the pseudo-random number thing, and out pops each time more and more different slots. So everything lands in A. The next one for A happens to be in slot 2. So it's slot 0 and slot 2. And then the next gap is to slot 5. So it's a bigger gap. And then it goes from 5 to 10. And then it goes from 10 to 19, and then 19 to 27. And so the stride is approximately 1.5 times, but there's randomness in there, which is driven by the pseudo-random stream. So it's repeatable every damn time. So now item B, same thing, but it's going to land in different places because it's got a different pseudo-random number seed. And so it's going to land in different spots, sometimes bumping into A, sometimes not. Add C, and it's the same thing, sometimes bumping into the ones that are there and sometimes not. But they get farther apart statistically, and the odds of bumping into things drop as you get to bigger numbers. Item D, same thing, always in 0, and then where it lands depends upon the luck of how the pseudo-random number thing generates it. These are infinite sequences. These are possible places that an item may live if you need it for a prefix. Doesn't mean it necessarily does. It means it might if you need that for the encoding. So here I have slot 0's got all 4 that I put in it. Slot 1's got 2. Slot 2's got 2. Slot 3's got C and D. It's got 2. Nothing landed in 4. Slot 5's got A. 2 landed in 6. 1 landed in D. And so the essential properties of this are pseudo-random number per item as a seed. So it's deterministic and repeatable per item. And exponential increase of slot indexes so the probability of collision drops rapidly.
If an infinite sequence doesn't necessarily make sense at first here, there's one perspective that you can take on this. If you're familiar with Merkle trees, you can imagine that the 0th sequence is capturing the subtree at the root, every element that's in the entire Merkle tree. As we walk down the slots, it's like we're moving breadth first across the tree. We're getting smaller and smaller subsets captured as the XOR of all of the items. What's different here, though, is that instead of being structured like a tree where every single subtree is discrete, this is instead randomized. It's basically like we're getting a randomized sequence of breadth first searching of a tree where sometimes we see elements show up in multiple subtrees.
Which is not what Merkle does. They don't show up in multiple subtrees in Merkle. So there's a notion of a generator. How can I find the items that are sharing the next slot? So if I can find the items sharing the next slot, I can XOR them together and I can make the next slot. Okay, so I can generate slots in the prefix. So think of an event horizon with the set of items in the next larger slot. Per item, generate the slot index in the sequence and keep a priority queue of what's next. So if I've got 4 things in slot 0, when I've put them in slot 0, I calculate where's the next place they'll land. So A's next place is slot 2, B's next place is slot 1, C's next place is slot 1, D's next place is slot 3. So I have a priority queue of the next stuff to do. So now I'm going to move to the next slot with some generated items, add slot items into it. Well, I had B and C, so I add them into slot 1, and then I move them forward in the priority queue. Then here I go to A and B, and then I move them forward. And as I continually generate that priority queue, things get less and less dense and they move out. And it's quite easy to think about generating the prefix pre-canned and then the ability to have the slot generator to move forward if I don't have enough in my prefix. So I can optimize this in multiple ways, but you can generate the sequence of slots and where things land and push them forward. And the next is a priority queue of the next slots. This is how one can think about taking a set of items and generating an encoding of where they smash together. Okay, so items and slots. Let's go into items and slots and what does that mean? So if I envision a slot in its sequence, let's just go to slot 8. It's got one thing in it. It's got C and it's got the hash of C. So it's got the item value, it's got the hash of the item. And I go to slot 4 and it's got 2 things smashed together. So I took the payload of the item C and a payload of the item D, XORed them together, whatever fixed length it is, it's fixed length. And then the hash of C XORed with the hash of D. So that's what landed in 4. And in 0, I got lots of crap smashed into 0. It's denser as you would go. So that's a way of thinking of the slots in the items. What do I mean by merge 2 slots? So this is a typo. It should say merge combines 2 slots by XORing their elements. So you XOR the item sum and you get a new item sum. You XOR the hash sums and you get a new hash sum. So if slot X and slot Y are two things I'm going to merge together. X has got items A, C, and D. Y has got items C, B, and D, and I'm going to XOR them together. Well, what happens is C and D cancel each other out because the bit pattern of the item of C XORs into oblivion with the bit pattern of the item of C, similarly D. So what I end up with is the combination of A and B XORed together. So this merge actually removes things, removes items that were in both, and adds items that were only in one. And so it has this interesting behavior of adding and subtracting things from a slot as you create a new slot by merging two. So let's talk about encoding and decoding. I want to encode a set of items one at a time. So I have an empty set. I add one thing in, and then I get it there, and then I add another, and I keep adding them one at a time. Start at slot 0 and merge the item into slot 0 by XORing the item and XORing its hash. If that's pure, if I've got only one thing in it, then I exit the loop. If it's not, then I go to my slot sequence, go jump into the future to a new slot, and keep merging until I find a slot where there wasn't something there first, and then I'm done. So let's start out. Let's assume I have A and B and D already present in an encoding, but I'm going to add C to the encoding. So these are the places that C might live, and that keeps on going. This is just the beginning of the places C might live in its sequence that's pseudo-random generated. So I add C to slot 0. I XOR it in, and I've got it there, but by gosh, that was not pure. Where's the next place? Slot 4. So I go there and I XOR it in, but gee, that wasn't pure. There was already something there. So I keep going. Where is the next place that I should put it? It's because 4 was not pure. Well, the next place in the sequence for C was slot 8. So I go to slot 8, I XOR it in, I say, wow, there was nothing else there. It is now pure. I have added C to the encoding. How do I decode? I decode a set by peeling. Because the encoded set has many slots, some's empty, some pure, some impure, I just keep going until I find something that's pure. So Daniel's sending me a prefix of an encoding. I'm trying to take it apart and find the items in it. I have to wait until I find one that's pure. When I find one that's pure, I'm going to decode it incrementally by generating its slot sequence and going back and then move backwards until I get to slot 0 and take it out. So I'm going to incrementally peel it out until I get back to 0. So I'm going to look for pure slots where the hash sum equals the item sum. Peel it back by merging it in, and then continue until I get an empty one. So let's show this. So I'm going to receive an encoded set, a slot at a time. Well, I get slot 0. It's got 4 things smashed together. That ain't pure. I'll remember that. Slot 1, that's not pure either. Skip slot 0 because it's empty. That's cool. Right? And I get to slot 3 and it's not pure. Slot 4 is not pure. Oh my gosh, wait. Slot 7 arrives because I skipped 5 and 6. Slot 7 arrives and it has a pure item B. That's cool. Now I can start making progress. So I peel, remember B, remember it's pure. I got B. I see it in clear text with the item value, and I start peeling it from the encoding. So I remember that I got B. I go and I want to follow the slot sequences for slot B. And these are the places B can land in its infinite sequence. Well, I'm on 7. I started at 7 with it being pure on 7. I go backwards to 0 from 7. So I peel it out of 7. Now it's gone. What's the previous place for B? Oh, it's slot 3. I've skipped slot 4. I go to slot 3. I peel it out of there, and it's not pure yet, but I see that peeling B out left A pure. So now I remember that A is now pure in slot 3. And I continue to peel B from slot 1 and slot 0, but I am not done yet. However, I've now got a pure A in slot 3, so I can peel it. So I start peeling B. I stop peeling B at slot 0, but I know slot A is pure in 3. Let's peel it from 3. So I peel item A out. I XOR it out of slot 3. And I end up with an empty slot 3. That's cool. XOR out of slot 1. I have an empty slot 1. And I XOR it out of slot 0. But slot 0 still got stuff, so I stop peeling A, but I'm not done yet. I don't have anything pure. Slot 0 and slot 4 have got multiple things. There's more than one in each, so I got to keep going for a while. So let's take more slots, and I get slot 8. Slot 8 is a pure C. I remember it. I peel it out of slot 8. I peel it out of slot 4, and I have a pure D. I remember D is pure in slot 4, and I peel it out of slot 0. And now I can go and repeat the process to take D out. So finally peel D, and notice the set is decoded. So I've decoded an encoding of this set. Now let's get to the magic. Let's show how you can do set difference in order n log n and how this is wicked cool. Do you want to say anything first, Daniel?
No, go ahead and move on to the next slide here, and then we can talk through it with the demonstration of the magic.
Cool. So let's take the set difference from a prefix of encoding. Say I'm sitting on server B and I got set B, and I have A, C, D, E, and F, and G. I got 6 items in there. And set A, Daniel's got set A, and he's got 4 items. Some of them I have, some of them I don't. I don't have B, okay? But I have the other ones I have that he has. And so he sends me his prefix. And so I take slot 0, I XOR it together, but I still have, it's not pure, but it's got B, D, E, and G. So if I want to look at reconciling slot 0, what does that mean? Daniel's 4 and my 6 have an overlap, but things that are different, okay? So if I XOR them together, what I see is the difference is there's 4 things that are in one set and not the other. So I got 4 things to find as we reconcile. Turns out it's B, D, E, and G, but I can't tell from that mushed up XOR yet. So that's what I'm looking to get as the difference. So now this slot 1 comes, and it's got, A, and I've got A, E, and G. So I XOR them together, and I end up with the difference between them is E and G as I look at the set difference. B comes, and it's pure. That's a pure thing because B and C come from A, but I XOR it with my C, and now I've got a pure B. So what happened is the things that were in common, the C in this case, they're disappearing into oblivion because they're XORed away. Now I received, after XORing it, a pure B. So I can take that symmetric difference, I can peel it out, and now it's gone, okay? But I still don't have anything pure, so I got to keep cooking. So what happens is I get slot number 4, or 3 rather, and I XOR them together, and what's remaining is the difference, which is E, because A and C and F are in both, and they XOR away. So now I take the E, and I peel it, and I take it out, and that's cool. But now I've realized I've got a pure G, so I can peel G and take it out, and then I realize I have a pure D. So in a mere 4 slots, I was able to peel the stuff that was different. And it wouldn't have mattered if the sets that were in common were larger. That's the difference I can do. So I have 4 items that emerged, and I have peeled them out by XORing them together. So remember how we had 1 item of difference when we XORed a million things together. A million items the same, 1 is different. The one that was different popped out. That's great. Remember that. And that was done in order 1 because of the difference. How about finding 3 items of difference? Slot by slot, XOR the sets. Turns out that the time to do that is order n log n of 3, or kind of 6 to 12-ish. And so you can see that the 3 items are different. So if I'm doing this together, and these sets are huge, there's an infinite amount of other crap that's in common. I got 3 things that are different, and it should take me about n log n of 3. So I get slot 0, I get slot 1, I skip slot 2, I get slot 3, and there I can begin to peel. So I begin to peel C, and then I have to keep going, but those are empty, so I can skip them, and then I get B, and I peel it out. And this particular PowerPoint example ended up with about order 7, which is about n log n of 3. So the bigger the difference is, it goes up by order n log n of the difference, not the corpus. You can have an arbitrary amount of crap that both of them know, and you don't see it. Okay, you want to say something, Daniel?
Sure, absolutely. So on the previous slide, putting this back into the tree contextualization, is that unlike other structures, as soon as you hit any layer that differs by 1, you can now recover the value. What this means in practice is that you don't necessarily need to do multiple round trips to recover more data. In this case, you just need a good prediction of how much of the prefix to send in the first place. So, for example, as a sender, I might make a pretty good estimate of what the difference is between me and my receiver. Let's say I expect that they might have lost up to 10 values. That's my best case prediction with 99% probability it's true. Well, then I can pick a prefix size and send it to recover those values. And if it's true that there's a less or equal to a difference of 10, it'll be able to accomplish this in a single round trip, which is an amazing difference
Single
compared to other.
unidirectional trip, actually. It's not even a round
Yeah,
trip.
it's not even a one round trip. Yeah, exactly. It's a unidirectional.
And then he's got it.
Yes. And then there's a variety of other techniques that you could layer on top of this to do even better for follow-up estimations. But this is the exciting part of this algorithm is that basically you can throw bits without knowing what the differences are, and the receiver can recover up to some amount of differences. They can treat this like an error correcting problem and just magically be able to recover the difference on their end without having to have any additional coordination.
And the math, if you have a pretty good guess, you can just talk about the probability that that's enough, right? And it doesn't have to be perfect because the other guy could say, well, I didn't quite get enough, send me more. And so that's just a little bit of a tax on top of it. But you can just do a very proactive just reconciliation. Here's what I got. Here's what I got. Here's what I got. And you can actually fine tune into guessing with the different guesses and just almost always make it be one blurb of a unidirectional send to make sure the knowledge is communicated. And that's pretty cool. Did I get it right, Daniel?
Yep.
So summary, practical rateless set reconciliation, new technique for set difference, low cost set difference in time, less than order n log n difference, not n log n of the set size. Leverages three concepts: per item infinite slot sequence, which is exponential and pseudo-random, always start at 0. XORing, taking that symmetric difference per slot, so the items in both slots are removed after XOR. And then pure slots start peeling items, so you peel the XOR to remove the impure ones. Each set has an encoding created for it. It's a flexible encoding. You can pre-calculate the beginning of it, so you don't have to do this generator for the beginning because you just pre-calculated it once. But as you need more, you can then take that generator and cause them to come as you need them. But pre-calculating is a great trick. It's like, here's my first 100, and then that just works. And if my first 100, if I add more items to the set, I can take the existing set and I can add those items on top of it. And my first 100 are pretty easy for me to calculate as I add items to the set, 100 being an arbitrary number. So reconciliation in either or both directions. Two different sets can be coming at each other and you just kind of mash them together and it works. You have a prefix transmission, so it's a prefix of this infinite encoding, and when enough, the receiver says stop. But again, you just guess, and you're pretty good if you do it right. And the receiver reconciles the prefix with a local set, which rapidly finds the difference. Each set can send batches concurrently, and it reconciles correctly. So this is pretty powerful. Now, we think there's emerging opportunities for this that are really great. And so, Daniel, you want to talk about the gossip protocols? I know you know this shit.
Yeah, absolutely. And I think this is one of the areas that would excite this group as well, because what's critical to this is agreeing on a set without knowing its contents. And a
Yeah.
wonderful way to do that is to use clocks and time bounding. That we can all agree that the set should be what we received in the last 10 seconds with a boundary condition of arbitrarily accurate nanoseconds. And it's this wonderful pair of hammers that we can hit a lot of things with, including efficient gossip protocols. Once you've built these sets, you can send them to many participants and be able to come to agreement across the distributed system very efficiently.
Who got what in what period of time is very interesting. Now, there is an algorithm variant that the paper goes into in depth, which I think is really cool. I would probably redo the slides to make it included next time around, which is to have a count field. So if I know how many items I've put in this particular slot, and I receive another image of the slot in a prefix encoding, and the count is different, you can subtract the count of what you're receiving from the count you have, and you can tell if you end up getting down to 1 in that count, if it was negative, then the item that you're receiving that you didn't have before came from the other side. If it's positive, then I already had it. So that's a really interesting thing, which is as you gossiping sets, a new incoming item, one you didn't have and what you've been listening to so far, ends up being negative. And so you put it there and you go, oh shit. So now you can detect what's arrived brand new into my server. So I have 100 replicas and everybody's just talking shit to everybody, gossiping. Each server will exactly one time see the new item pop up to be processed. Now, the ordering is not the same necessarily in each one, but they pop up efficiently, super efficiently, exactly once as you gossip. That's pretty dang good. That efficient gossip is, I think, going to change distributed computing over time. It's really cool. Daniel, you got anything you want to add to that?
Let's jump to the next slide.
Deadline based. Go for it.
Yes. So this is the crux of why I think this audience will be interested, because really this changes that worldview of we need to order everything ahead of time to have efficient reconciliation, and instead goes into a more partially ordered worldview, which is we would like to be able to distinguish between things that happened in the future and the past, but we're okay for some of these things happening concurrently. We can use these error correcting codes to be able to recover a perfect view of the world of some previous epoch. But this means we shift into a partially ordered world where the two tools at our disposal are deadlines and error correction. And how are we going to do this any other means than having efficient and accurate clocks?
But if you want to adjudicate what made it in what epoch, what window of time, if you want that perfect truth of this is exactly what made it, and this is exactly what didn't, you can choose to have a timekeeper server. And it takes whatever it got when its time is in this window of time, and it closes that set, closes that epoch at that point in time, and says, here is what made it and here's what didn't. That's one technique. If you want to avoid jitter on that, you can actually make the timekeeper be a quorum of a set of servers. And you can actually say something made it if it made it into 2 of 3 or 5 of 9 of the servers that I have. And then that defines it made it or it didn't. That gets fuzzy if you only have a subset of the knowledge, because you actually have a tri-state. You know the things that made it for sure, absolutely. You know the things that didn't make it for sure, absolutely. But if you can't talk to enough servers, you might have a little confusion around the edge. But it's super useful for many algorithms. And you can define the bands of time, like I do a millisecond band, and then I've got the 10 millisecond unioning of those bands, and I've got 100 millisecond unioning of 10 bands, that class of things. You can think very differently about deadlines. That allows you to rethink common knowledge, which is a fascinating thing. Closing a deadline-based set is, I know what you knew. I don't know what you know because time's gone by, but I know what you knew up to that deadline. And you can adjudicate transaction commit with optimistic concurrency control, and useful for many distributed systems algorithms. I know Daniel wants to talk about that.
Yeah, absolutely. So that I think this is the one of the big hammers that we've been excited to run around and hit things with, because you can recapture a lot of existing protocols. Like a good example is something like two-phase commit, which we'll talk again a little bit more about in the next slide, as a mutual knowledge problem. That what you want to do is make sure that all the individual servers don't act unless they have knowledge about the state of the others. But instead of having this be done on a piecemeal basis, the normal way is that you send out, your first round of communication, and then your second round of communication adds the information about what all others that are present. You can have an inferred batch operation. So instead, you send all of the information to all of your servers to say, oh yeah, we would like to, our goal is to commit some value. And then you perform a round of reconciliation. Any disagreements will fall out from this, but all of the agreements
they disappear.
XOR away.
The XOR it is all the shit that you agree on just goes away fast. Yeah. And the only thing you have to look at is the crap you got to clean up, which is the stuff that didn't go away fast. That ends up being super interesting and powerful. I want to point a different thing out. Okay. This opens up a whole different style of computing in cloud computing. Cloud computing is weird. It's fun. It is weird. You separate the server state from the compute, and compute and storage are separated. The classic way we do this is you take a set of virtual servers, you find compute, and when they make changes, you're logging the changes to, things like EBS or other things like that that are capturing a log-based sequence of transitions this server took. And so you can think of this virtual server as freeze drying and popping up somewhere else. Today in the cloud, you typically have log-based state of the separated storage and compute, and the single history of a server can be reconstructed on a new compute instance. I think of this as like Captain Kirk in the Starship Enterprise. You're talking to James T. Kirk, and he says, "Beam me down to the planet, Scotty." Right? And then he has a couple of seconds where he kind of goes into suspended animation, and then he appears down on the planet with all of his memories and all of the decision making, all of the algorithms that are going to decide what he does in response to a circumstance. Just moved, but he stopped and he moved elsewhere. And he has a total order of memory and personality as you beam him down. That's what we do in the cloud. We emulate classic distributed computing with a server in a closet with direct attached storage. We emulate that, separating compute and storage into a log-based thing with a total order on a per server basis. If you rethink the algorithms to be set-based, then tomorrow items arrive in a set in any order, and its deadline-based close can provide order if needed. And so set-based cloud implementations can be more responsive and robust if you rethink things as sets and arrival of items into sets. Daniel,
So,
go.
yeah, so let's bring this into concrete terms. As you can probably tell from this presentation, this is a hammer that got us both very excited, and we've been running around trying to find what nails we can hit with it. One of the first things we brought up with this was anti-entropy. There's a lot of existing systems that one of the callouts here was Cassandra, but a variety of different systems that use this. And it's very exciting to be able to reapply this as potentially more efficient anti-entropy systems. The other classic example is quorum evolution, which we can use to use these algorithms to do standard things like catching up replicas from a restored snapshot, or potentially even more bizarre things like doing uncoordinated data discovery, where you throw in a replica and you find out what it knows and the rest of the system doesn't. And then lastly is the one that we alluded to here, which I am definitely the most excited about, which is re-implementing multi-phase protocols using inferred knowledge, where basically that you can infer agreement because all of what was XORed away. You can essentially patch this on top of existing systems that don't have good consistency semantics, and have a one-round version of a one-round coordination to say, great, let's assume that there's some errors. There's inconsistency between our replicas. Let's resolve that and say that we have a line of epoch that is consistent, and then we have a epoch line that is inconsistent. That this very common knowledge focused view of protocols and inferred agreement is really exciting, and is fundamentally the combination of error correction and time bounding with clocks.
Then that's super interesting to think about that as a variant of consensus, variant of two-phase commit, all these things. Yep. So conclusion. In the past, databases adjudicated change. Arguably now with sets in this fashion, they can discover change, not just the transaction log. I'm going to say efficient event processing is emerging as an important pattern. Vibrant sets of knowledge rapidly visible to many servers. Let me just throw a random crap out here. The Large Hadron Collider generates like millions of things that are not relevant, and you want to find the one in the millions that is worth paying attention to. So as these events fly by individually, you can drop them into a different set, which says this one has these characteristics, and now you put it in a different set. But and you can do that redundantly filtering. There's a ton of things you can do if you just think about events and items and qualifications of what fits into what set. And the nature of defining empty sets that make sense is going to be fun and fast. Fast reconciliation can change the nature of dynamic systems. And finally, I'm going to make one other point. I'm a database distributed systems person, but I was not beyond looking at SIGCOMM to see what interesting papers were there. Pay attention to other things in the industry. So now let's have a discussion. Let's stop presenting. Let's start talking. What do you guys think you can do with this crap? I want to see faces. Turn cameras on. Talk to us.
Thank you. All right. So it looks like the condition to ask question is turn the camera on.
Turn the camera on. For God's sake, turn your camera on. You've been looking at my ugly mug.
Bishop, go ahead.
I am on
your
my
camera
bed.
should be on.
I am on my bed, man. I don't look good. Anyway, so the question
come
I
on,
have,
we'll leave that up.
so we'll meet face to face, sure, in the future, near future. I'm thinking this is all great, but I'm thinking of practical implementations for all of this, like in security, for example, synchronizing keys or something like that.
Hell yeah.
Like, for example, when you use something like keys resource management protocols. Maybe it can make use of this.
I don't disagree. I do agree. We did
Yeah,
this crazy thing. We don't know what to do with this stuff. And so we're being open about our ignorance and open about our excitement about the fact that there's gold in them hills. And key reconciliation, sharing knowledge, that's phenomenal.
so if this is the case back then, I would think RBKI is a good example of to apply the algorithms you described to
What was again the thing
synchronize
I don't know what you're talking about.
uh, uh, R like Roman, P like Peter, KI
Oh,
resource public resource public
BKI.
key.
Fine, sure.
Yeah, I think this would be a good application for what you described.
I have no problem with that.
Good,
I'm
good,
completely comfortable with that. That's just one of a bunch of things. I
exactly.
want people to be excited about how to do this in different ways.
Yeah, excellent, excellent.
Okay, so I want to add something. So for me, like, if I see something and I get reminded of old stuff that I've seen somewhere. So we learned about this thing called Katapayadi system, and I put a link here. And this comes from, an old system where they used to have Sanskrit encoding of knowledge, and that was there was an error correction system built into it.
Sure.
And that is something which I see here that you were just presenting in the paper. So I haven't, of course, looked at all the details, but I got reminded of it. So I just put it here. It seems this was similar to what they were doing when they were encoding knowledge for certain things like the value of pi, which is encoded in Katapayadi to like, hundreds of digits of pi. And so they would just encode it in a way that if there was some, thing that changed, it would just not add up to the rules. And so they couldn't detect it. So
This is
just
neat.
wanted to
I
add
had
that.
no idea error correction went this far back.
That's
Yeah,
awesome.
yeah, they had amazing
so
error
cool.
correction there, right?
That's
And that was why they were like so particular about like, okay, when you chant a particular Sanskrit mantra or something, it has to be set with the right tone and
Cadence.
right, all those things, because that's encoding. And if you
That's
don't say
lovely.
it right, it is just going to be wrong. So
That's lovely. My brother Andy annihilated my Hawaii vacation once and it was joyous. I went and I spent 5 days sitting on the lanai at the condo we rented, reading about fountain codes and Luby transforms and how to do forward error correction and messaging. And I was just gobsmacked about how cool it was. And this is the same and different. This is even more. But
right,
the whole
right.
notion, and we haven't talked enough about what happens if you send a prefix of an encoding and some of it's damaged. We have not thought enough about that.
This is beautiful. This is just beautiful. Like, this opens up so many possibilities of thinking, I'm just
Right.
excited.
I
I'm excited.
personally love the fast and loose interpretation of this, where there's a variety of different databases and distributed systems that work most of the time. That they are not necessarily correct protocols, but that they solve somebody's real problem. That it would be really fascinating if we can treat this sort of like how error correcting codes are treated in networking, where instead it's some patch that you put underneath existing systems, where we have a clean layer of abstraction to basically fix systems that work most of the time.
Well, I'm fascinated by building a control plane for a cloud system. And all the just things you observe are just propagating accurately, but not in order. Not in order, but accurately. They're going to be in this. You can even time bound their arrival by dealing with what does time bound means? It means this server knows it's seen everything up to this point in time, whatever that means. But thinking that through, how time weaves together with this, are just at the beginning of this. And this is not deeply related to our day job, so we get distracted and find time on the side to work on it. But it is exciting enough. I want to find some nerds to bond with on it, if that makes any sense. Okay, so other nerds, talk up. Come and speak up. Who else has?
I like, I mean, I came in halfway, but looking at what you were showing, it reminded me of a couple different things. Like, I worked on network coding and, some other things that really struck me as kind of from the same tree almost, because a lot of that is set theory and a lot of it is kind of, gathering information in grouplets, if you will, and so on. So but what I was, if I'm surmising correctly, the information rate improvement here is pretty high. There's a lot of gain, right? So
The paper digs deeply into that. I was a little less stressed about the density of the encoding myself because I wanted to see more about how to think differently about sets, but there's a ton of stuff in that paper in SIGCOMM, called Practical Rateless Set Reconciliation, about how to titrate towards the Shannon theoretical limit of information encoding. And Daniel understood that better than I because he's not as ignorant in math as I am. He knows a lot about math and I don't.
So that's the opiate of the people like me who like to go and develop protocols. It's like, hey, there's a pot of gold at the end here, or a very small pot of gold, in fact. But that's something that caught my eye, and I'm looking forward
Not integrating that Shannon theoretical information limit and the error correction by any means. I personally am excited about how to use it in a way where the systems are interpreting their communication differently. But that doesn't take away from what you just said at all. Go read the paper if you want to go deep into that.
It's also the case that the specific algorithm that was used is likely in a very large family of them, because it's not that different from, as you mentioned, the fountain codes or other error correcting codes that exist. It's using the same concept. The main philosophical difference if you're setting out to design a protocol, is that instead of treating this like a recovery problem, where basically that there was an original signal or an original set of bits that were written to a hard drive that you are going to then have errors accumulate and you want to recover, instead it's treating it as there's some mechanism that we used to agree that the right answer is the union of all of our sets, or really any operation that is but the point is that you've come to agreement on what the correct value is. It may not have been an original version, an original encoded data, but you can still use error correction to basically marshal your system towards that target. But that's it. It's all the same mechanisms. It's just the error.
There's a whole world of defining future non-existing sets, and the metadata exploration and the ontology of what it means to agree in advance that in the future, this is the set where these things will land. And that's set with time, that's set with filtering and characteristics, that's set with sets with whatever damn properties we want to define. And there's an unexplored space of thinking about empty sets that can be filled over time, and then propagating when they do. I haven't figured it all out. I'm excited about it, and I scratch my head sometimes when I'm wandering around and pissing my wife off as I look at the ceiling. But this is a thing that rattles in my head: is what is that ontology? What is that metadata exploration? How do we create an open-ended thing to think about that? Did that make sense when I said it? Both time and space, and go ye forth and view it as a tensor space, for God's sake, of sets, and think about what gets dropped into what. Did my imagination make sense to you guys? Hey, Madhav, you joined. Thanks. You pinged me earlier. What do you think? Am I on drugs, or should I be? That's the
no.
Pardon me?
No, I mean, I found it really interesting. And thanks for sharing the link. I mean, this is super interesting. I think about these things a little bit more these days. But I think it's very interesting to think about what you said, right? Like having potentially empty sets that you can fill in at a later point of time, or and then propagating that forward. I think that's exciting to think about. It sort of reminds me a little bit, at least, like the notion of it. The one of the more recent works by Berkeley and Hillestein, Keep Calm and CRDT on.
Oh God, yes. That's based upon shit that I did back in the day.
Yes, yeah.
I love that stuff.
Yeah, I think that's it's just nice to see things connecting, right? So I'm excited to see where things go.
I wrote a little bit about that in a paper I did called "Don't Get Stuck on the Con Game," which talks about the ambiguities of consistency, convergence, and confluence. And there's just fun stuff in that space, which is related but different to this. Both, they're kind of a duality.
I think it was about a year ago now at Cider that we were talking, without the existence of this paper quite yet, but this principle of, if you could infer mutual knowledge and basically these types of mechanisms with the same group of folks, So I'm really excited to see what they end up coming up with, because a lot of this is very related, that seeing the junction of error correcting and inferring knowledge. I've always really appreciated the Berkeley crew's perspective on how these are
They're
deeply
fun.
related to common knowledge problems.
Oh, they're tons of fun. And my CIDR paper from January of this year, which was called, Scalable OLTP in the Cloud, What's the Big Deal, is all about how can we reason about a scalable transaction system and detect conflicts on key conflicts and detect within a bounded window of time, how can we know recent changes to sets of data? And so all of this is still nascent, and there's tons of future in this. It's an exciting time to be a nerd.
Totally agreed. Madhu,
I
do
think
you know your name coincides with the mathematician who actually came up with error encoding in India like
Oh,
2,000
really?
years back?
Oh, wow, that's interesting.
Yeah.
That's good to know.
Yeah.
That's cool. That's cool. Well, I really want to thank you guys for your attention.
I think a bit one of the good things about your presentation is that you used animation to
Oh, that's
describe what is difficult stuff that you might not be able to get when you read the paper, like how to understand the rateless invertible bloom lookup tables, which is the main contribution of this paper. Really, you explained it in a way very good to understand by anybody, step by
don't
step
misunderstand.
animation.
Thank you. I spent many, many, many hours fiddling with PowerPoint,
I know, I know.
and this presentation, I needed two laptops, one for the screenshot of PowerPoint so I
Yes,
could animate. And so no, I but
yeah,
I believe people's time is worth investing in making their time efficient. And I try to.
exactly,
The
exactly.
Animations were fun. Yeah.
Yeah.
Is
So
this
if you
presentation going to be available or?
We have not yet. We're kind of fine tuning it, honestly, and learning and adapting it. And I was just right before the hour talking about this with, okay, Daniel, let's sit down with damn PowerPoint and put our little faces in the corner of that thing. Literally, when I emptied out at an empty presentation, I put the box in the corner, knowing precisely the size of the video of your face that PowerPoint will record in anticipation of doing that, and then pushing it up on YouTube so it's available. So
Cool.
that's planning it. And because I've been there, done that, got the T-shirt. If you want to know the extent of it, go look at my blog and see the video of the I'm so glad I'm uncoordinated from a couple years ago, which had even more sophisticated animations. And so, because sometimes when you fiddle when you're thinking, drawing animations is kind of my fiddling when I'm thinking sometimes. So, but thank you. I'm glad you enjoyed it. I know I pushed a lot of content in a little window of time.
Yeah, but the animation makes it easier to understand.
Thank you, and I agree.
Yeah, yeah. When I looked at the YouTube presentation for the authors in the SIGCOMM conference, it wasn't that easy to understand, to be honest with you.
The paper wasn't that easy to understand.
I
However,
know, I know,
there's a
I know.
ton of really good stuff on the Shannon theoretical
Yes,
and limited.
yes,
So, and believe me, Daniel and I were arguing about this for months before we knew how to understand it and then explain it. So we had a lot of fun, by the way. It was a lot of arm wrestling between the two of us. It was fun. I mean,
yeah.
so
And the supervisor for these students is Muhammad Ali Zada. He's a very, very smart guy.
very smart guy. And I'm not done. Oh, the
Very
paper's
smart guy.
great. But
Yeah,
I'm actually trying to come at it from a distributed systems perspective a little more than a data communications. But there's gold in that paper.
yeah.
So
And their claim is right. They have the first universal sketch for or algorithm. Really, nobody has done it before, right? That is their claim, and I think they're right.
and I want to acknowledge what they've done, but I want to slice
Yeah,
it a little different in a perspective. Both.
yeah,
I think that this is an area where they did an amazing job of connecting the dots, because uh, Ken Berman brought to our attention that there actually might be a few papers that were similar to this, but never achieved the same efficiency, that were sort of lost to time. That, but this is the first time that we've seen the real connection of error correcting code, basically just erasure code research, and what you can do to implement set reconciliation with it, and actually achieving the full target efficiency.
And
Exactly.
I fully believe that if you have set reconciliation, you can build everything else on top of it. That's just fine.
I agree. And also they provide good balance between computation and communication efficiency.
Yep.
Or other algorithms, I don't see that. So that is also good contribution.
Yep. So I just want to get everybody excited and people do good stuff. And let me know if you got some ways to improve on it and bounce around if you want to be a nerd together. I'm a nerd. I want to do nerd shit with people, if that makes any sense. So thank you, Ahmed, for including us. We
You're very
appreciate
welcome.
it. I appreciate it.
So next talk will be January 1st, will be basically next year, by Paul Borrell about Ethernet space-time. And Paul, do you want to give a preamble before we close, or you want to keep everyone surprised?
Right.
No, actually, we're going to be announcing something called Ethernet 2025. And just to let you all know, we've been working on the Shannon set reconciliation problem for years and have made some significant progress in the last year. And really what we're looking at is the notion of time can be expressed on Ethernet. If you can have essentially different numbers of fixed size objects, the slots that Pat is talking about here, basically for just entanglement, you can do it with 4 slots, and for actually doing a 2-phase commit, for example, you can do it with 16 slots. And to do more advanced multi-phase protocols, you can have any arbitrary amount of, basically it's a Hadamard number of slots. And so this set reconciliation algorithm fits perfectly with what we've begun to understand from the physics perspective. And just let me give you a little bit of interesting pieces here. One of the things that the quantum guys have actually discovered is this thing called forgetting. Apparently, if you forget things, then you are basically causing the causality to do different strange things to you. And also dropping, if you drop packets, for example, or if you forget things. Forgetting and discarding are the 2 key issues that's being thoroughly investigated right now by both the experimentalists as well as the theoreticians in the physics community.
I'm looking forward to this on New Year's Day, because with being hungover, it should make more sense. But I got to go right. I'm looking forward to it. New Year's Day. Let us know.
All right. Thank you, everyone.
Thank you, everyone.
See you on New Year's Day. Bye.
Happy holidays.